In this video, we'll look at maximum and min values and how calculus can help us determine these things. So I drew like a typical graph here. There's different definitions that you really need to keep clear. They're written really clearly in section 4.2 in the book. And it's worth looking at those to make sure you keep these things straight. I'll try to go over them here. It gets a little bit tricky. Okay, so let's look at this curve. First, there are absolute minimums and absolute maximums, which is the biggest this curve gets and the smallest it gets. And I'm stopping it, right? This won't go to infinity. If it went to infinity and just kept going down forever, then there is no absolute smallest. It goes down forever. It's negative infinity, which generally doesn't count. Or positive infinity if this went on forever, which would be the absolute maximum, which generally doesn't count. We want to have a nice number, not infinities. But I stopped it off, all right? I chopped it off here and chopped it off here. So the absolute minimum is the smallest this gets. This one does not have one because I put an open circle. We can get closer and closer and closer. There's no number we can say is the smallest because we can get closer and closer to this point, but we can't get to that point. So in this case, the absolute, the smallest point on this interval doesn't exist. What is the biggest point? In this case, it does exist because I put a closed dot where it ends. So the absolute maximum, the biggest this gets, is that point there. Let's say that's, I'm just going to make it up, let's say that's at 10. So we'd say that's 10. Okay, then there are local minimums, which means on both sides it's the smallest on both sides. So maybe looks like there's one right there and one right there. Okay, so this is a local minimum. This is a local minimum because it's the smallest on both sides. If this was a closed circle, it would not be a local minimum because it's only the smallest on one side. It doesn't go further. It would be a minimum, but not a local minimum. Because local minimum has got to be like a trough, right? And even here, okay, this is a sharp point. The derivative does not exist at a sharp point, but it's still a local minimum, right? It's the smallest here. It goes up, goes up. So we have local minimums right here and here. Let's make that up. Let's say this is x equals 5, and let's say this is x equals 10. So the local minimums would occur at x equals 5 and x equals 10. Now how about a local maximum? They would occur, of course, right here at this peak and that peak. Again, the tallest on the other side. They're not the biggest. This is the biggest, but they're local maxes. And let's say that's at 3 and this one is at, I don't know, let's say it's at 7. So we would say at x equals 3 and x equals 7 we have a local maximum. We could say what it was if I made up a y value. Whatever, you get the idea. The peaks are local maxes, troughs are local minimums, and it can be a sharp point. Even though the derivative does not exist at a sharp point, it's still a local min or max. Okay, then there are things called critical points. So critical points are when the slope is 0 or doesn't exist. Okay, which means it's a max or min. Right? So max or min or sharp point, that could be that case, right? So sharp points are examples of those, max or mins are examples of those, but it also can get pretty tricky for critical points, so we got to be a little bit careful. Typically, though, a critical point is when we get the slope is 0 or the slope doesn't exist, which means that the derivative, so f prime is 0 or the derivative does not exist, because that's what the slope is, right? The slope's the derivative. So critical points where the slope is 0 or the derivative is 0 or doesn't exist. So to find critical points, you take the derivative. Where is the derivative equal to 0, or where do you generally divide by 0, or you get a sharp point like that? Those are called the critical points. Now, oftentimes there are maximum minimums. But there's always the weird ones, right? So one way for the derivative not to exist is if it's discontinuous. So if we look at critical points, let me draw a new graph here. So let's say here's our graph, and it jumps from here to here. So actually, let's make it even more clever. Let's say it goes the other way. Let's put an open circle here and a circle there, and then goes down, and then we have a sharp point, and then it goes like this. That's a tricky one. Okay, this point here, the derivative doesn't exist, right? I mean, it's discontinuous. So this would be a critical point. Let's say that's 3. And let's say this is 7. That's a critical point. The derivative does not exist. It's a sharp point. Right here, let's say that's at 9. There, the derivative is 0. So that's a critical point, but it's not a maximum or minimum. So here, right, the derivative is 0 because it's flat, but it's not a max or min. So you got to be really careful. Just because the derivative is 0 doesn't make it max or min. Now if we did this, right here the derivative is 0, and it is a maximum because the slope is flat there, right? There's a 0 slope, and it's the biggest in the area. It goes down on this side, goes down on that side. So that's definitely a critical point too. Let's say that's at 11. So in this case there are 4 critical points here where it's discontinuous, the derivative doesn't exist. Sharp point, derivative doesn't exist. Here, slope is 0. It's a critical point, but it's not a max or min. So again, just because the slope is 0 does not mean it's a maximum or minimum. And here is a normal critical point where it's a local maximum. And this is also an absolute maximum. If we stop the function here and here, this is the bigger it gets. So it's a local and absolute maximum. So those are just some definitions that you'll play with. A typical problem in this chapter is something like this. They'll say, and this is number 24 in the book, so I'll just say, so they'll say f of x is equal to x cubed plus x squared minus x, and they say find the critical numbers. So critical numbers and critical points, okay, same thing. So critical numbers, critical points, I don't know, you hear it's the same thing. So what are the critical numbers here? So what you do is you take the derivative, set it equal to 0, or take the derivative, and then you can set it equal to 0 to find where it's 0, and then also find where it might not exist. Okay, so if you're dividing by 0 or something, usually that's when it doesn't exist. So let's take the derivative. So f prime of x is 3x squared plus 2x minus 1. We set that equal to 0. Okay, first, there's no place it doesn't exist, right? This is just a nice simple polynomial, so you don't have to worry about those. So now it's just a matter of using hoping it factors, or we use the quadratic formula. Looks like it's not going to factor, so we have to use a quadratic formula. So where does that equal 0? X is equal to negative b, that's negative 2, plus or minus the square root of b squared. 2 squared is 4, minus 4ac, so 4a is 3, c is negative 1, all over 2a, a is 3, so 2a is 6, so that's equal to, let's see, negative 2/6, or negative 1/3, plus or minus the square root, let's see, it's plus because it's minus and negative, so 4 minus plus 12, oh, that's nice, which is 16, which is square root of 16 is 4. So plus or minus 4/6, looks like, if I did that right, 4/6 is 2/3, so it's negative 1/3 plus or minus 2/3. Let's see, when it's plus 2/3, it's 1/3. When it's minus 2/3, negative 1/3 minus 2/3 is negative 1. So this has critical points of 1/3 and negative 1. There's no places where it does not exist, and we assume it goes on forever. There's no endpoints or something, which aren't critical points anyway. It's only where the slope is 0 or the slope doesn't exist. Okay, so that's an example. You basically just take in derivatives, doesn't equal to 0. And of course it can get trickier. You got to use product rules, all that kind of stuff. So yeah, and also if it doesn't exist. So let's do a harder one, like number 26, which says that, no, not 26, number 30. 30 here, which says that f of x, I'm going to change to x as a p, is x minus 1 over x squared plus 4. So we got to take the derivative of this thing, which is going to be a pain. We have to use the quotient rule. So f prime of x, you got to remember these rules. The derivative of the top, oh, that's easy, it's just 1 times the bottom, x squared plus 4, minus the top, x minus 1, times the derivative of the bottom. The derivative of the bottom is just 2x, divided by the bottom squared, x squared plus 4 squared. Let's simplify the top here. That's x squared plus 4 here, minus 2x times x, which is minus 2x squared. I believe minus 2x, yep. And then minus times minus is plus 2x. Minus 2x times negative 1 is minus 2x. Yep, that's right. Divided by x squared plus 4 squared. Okay, one more simplification here. X squared minus, let's see, 2x. Okay, that would be negative x squared. Negative 1 wins. Plus 2x plus 4 divided by x squared plus 4 squared. Okay, we want to find the critical points. Where is this 0? This is 0 when the top is 0. Or if the bottom is infinity. But we're not going to go there. Sure, x equals infinity, we get 0 here. But actually maybe not. Well, yeah, because it's squared. But then you have to take the limit. Anyway, we're not going to go there. What you always do is to make this 0, the top has to be 0. And to see if it doesn't exist, we got to put where if the bottom can be 0. But the bottom can't be 0 because this is, if it was x squared minus 4, then at x equals 2 we'd be dividing by 0. But x squared is always positive, 4 is positive, squaring it's always positive, so we don't have a does not exist in this one. Again, this would have been more interesting if they'd put a minus 4 in the bottom. Then we'd say, oh, x equals 2 is a critical point. So all we do is we go negative x squared plus 2x plus 4, figure out when that's equal to 0. We'll probably have to use a quadratic formula again, and we find the critical points. So that's the idea with that one. And let me do one more really quick. They say, like for number 38, they say find the absolute max and absolute minimums on a given interval. Okay, on a given interval. So this is like 38. So they say 38 is f of x equals x cubed minus 3x plus 1 on the interval 0, 3. Okay, so what you do is first we just do the normal thing. We say, okay, let's figure out where it's 0. So we take f prime of x, which is 3x squared minus 3. Okay, that's the derivative. Now, there's no place where this doesn't exist, right? There's no dividing by zeros or anything. But we want to find when that's 0, so we set that equal to 0. And now let's see, so divide both sides by 3, so we have x squared minus 1 equals 0, x squared equals 1, so x equals plus or minus 1. Okay, so that's definitely in between, oops, but look, it's only between 0 and 3, so negative 1 doesn't work. So really it's just plus 1. Because negative 1 is not between 0 and 3. So there is either a local maximum or a local minimum at x equal 1. So that's what we know. Now, if we want to find if it's the biggest, okay, so let's see what is it at x equal 1. We plug it back into our normal formula here. And at x equals 1, it's f of 1 is equal to x cubed, 1 cubed minus 3 times 1 plus 1. So 1 minus 3, 1 plus 1 is 2 minus 3, it's negative 1. Okay, so that's one point of negative 1. So is it an absolute maximum or minimum? The other what we have to do is figure out what it is at the endpoints. Okay, maybe at the very end of this interval it's the biggest. So what's f of 0? So f of 0 is 0 cubed minus 3 times 0 plus 1. which is 1. And what's f of 3? So you have to look at the endpoints as well as whether the derivative is 0 to see if it's a local max or min. And f of 3 is 3 cubed minus 3 times 3 plus 1, which is 27 minus 9, which is 18, which is 19. Okay, so this would be our absolute minimum. That's the lowest it gets. This would be our absolute maximum. And that's just a point at the end that isn't the biggest or the smallest it gets. We also know that f of 1 is also going to be, well, actually, we don't know if it's a local minimum. Maybe it's one of these things. Maybe it's something like that, and maybe it's not a local maximum or minimum. So we can't say that. All we know is that that's the smallest it's going to get. Because it gets down to -1 there. Which actually, if it gets down to -1, really can't be something like that, right? So I guess actually it has to be a local minimum because it's the smallest it gets in between there. Yeah, okay, so that's how you do these. It's pretty tricky sometimes. You got to think about what's going on. And Desmos is your friend. It's okay to graph these things. Use Desmos to see what the graph looks like to check your answers. Be careful of where it's a boundary. It's on, they're only looking at a certain place where it's not doesn't go on to infinity. We're only looking between 0 and 3, so you got to check what it is at 0, check what it is at 3, see what's the biggest. And again, use Desmos and graph it to help you figure this out. All right, thanks for listening.